Okay. In the second place, we may have another topic about the what, about the, I'm sorry, okay, unity feedback system in here. For example, for the unity feedback system of GS is equals to the what, the K divided by S plus 3, S plus 5, okay? And find the range of gain K satisfying stability, but using the what? Using the Nyquist criteria, okay? Solution can be applied that firstly we need to assign first K equals to the 1 with GS times HS is equals to the what? 1 divided by S plus 3, S plus 5. Okay, HS is equals to the 1 because it's a unity feedback. Okay, and then apply S equal JV. Then we have GJW times HJW is equals to the what? The 1 S plus 3, S plus 5, and S equals to what? JW. And so in the absolute form or the magnitude form, we have the minus 8 times W square J 15W W over 3, and also 64W W over 4 plus W over 2 minus 15 minus W square and square. Okay, and so in the first place we need to give the what at W equals 0, and then GJW HWG is equals to what? The minus 0 0 3 5 6 minus J infinity. Okay, at this one, because of this the what? This the zeros. Okay, at 0, and this the 0, and this the 0, and also 0, and also 0. Okay, and so for imaginary part is equals 0, and then W can be found as the SQRT or square root of the 15, because we have this information in here, 15 times W minus W over 3. Okay, and so then we can put this value into the what? Into the R transfer function, and we have minus 8 times square divided by 64 times square root of 15 over 4, and so this is equals to what? The minus 0.0083. okay, our transfer function is that. And so what is the condition of the R stability in here? Just like this one, because so we need to examine the imaginary part of these terms, because it must be equals to what? The real is the 0, and then we can check that the minus 1. And so how can we do that to be not encircled to the minus 1? And so the K can be calculated with what? The 1 divided by 0.0083, which is equals to what? 21 120.5. okay, and so for the stability we need to provide that the K is smaller than this one, because this is equals to the what? At the K, for example, this is the unity K, but if we change this value with the K, and so this increased also to what? at the -1. Okay, and so we can say that this stability can be accomplished by using these denominations. Okay, so how can we be sure about that? We must go to the Nyquist plot examples. K is equals to 1. Okay, and numerator with the with the K, and denominator is equals to the 1, 8, 15 and 0. This is the solution of the s, these values in here, s plus 3, s plus 5. Okay, and so this is the multiplication form of these terms. After that, the g is equals to the tf num, and then okay and the Nyquist g, the grade on, can be given in here. And so if I run this code, and then we will have this information in here just like this one, and so the -1 is given in here. See, but what is the values of these terms? Just see that. See, this is equals to this is the intersection point of these curves. This equals to -8.22, which means that if this relating to the imaginary gives us the 0, which means that we have the only real part of this system. See, the imaginary part is 0 at this place, and so we can search the real part of the R system, which means that if we set the imaginary is equal 0, and then we will get the frequency values of these terms, and then we can give or search to the intersection points of these terms. Okay, just like this one, this intersection at the -8.2 times 10 over -3. Okay, and so if I put to this k is 120, and then if we apply this condition, and so what is the values of the -1? See that this -1 cannot be interchanged between these two answers, or we cannot rotate about the -1 in here. But if I choose for example 122 in here, and so if I run this code, and then we will say that the -1 points in here at the encircled form of this nomination, because the encirclement is about in here, but the -1 in the circle or the contour. Okay, this is how we can check the R stability on the Nyquist plots in the MATLAB. Okay, so what's the other point in here? Firstly, we can use the Nyquist plot in here, or we can plot the R Nyquist with the manual calculations. How can we do that? In order to understand it deeply, to draw the Nyquist plot, and then we can define just like the body plot. Just remember that we can draw the body plot by using these cases. We can update or calculate the magnitudes and the phase, and so we can draw the whole values based on these terms. But how can we draw the Nyquist plot automatically? Firstly, we need to define the unity gain in here, just like this one, and so the omega should be log space between the -1 to 2 and 1000 points, which means that we have the 0.1 to 100 radian to second can be given in here. Okay, and so how can we return to the points of the S must be equalized with the 1i times omega, right? J omega can be given in here, and so GS can be given by K dot divided by S dot times S plus 3 dot times and S plus 5. Okay, this is the solution for or conversion of the what the GS with the what as equals to the J times omega. Okay, and after that we need to search the real part of this system. The real returns to the what the real part of the GS. Okay, and so also we can give the imaginary part of this system, imag, and this is the imag. Okay. These are two terms, okay? And so we have the imaginary and the real parts, and then we can plot these values, just like this one. The Nyquist plot is manually equals to the what? The figure of the plot real part and the imag part, right? And hold on, also plot to what? To its symmetry, real part minus imag part with the notions of the R, okay? And so the X label can be given with the real axis and Y label is the what? The imag axis, okay? And so the grid on the axis must be equals in here, okay? And also we need to give the plot for the what? For the -1, 0. This is our stability region in here, and KO, the marker face color must be assigned with the K, okay? And so the legend should be given in here, J omega, right? And also the conjugate, J omega. This is the simplest way to what? To draw the Nyquist plot in here, just like this one. See that? It's R, the what? The complex conjugate formulation, and so this is R, the what? The R normal real part of this study, okay? And so if I put the what? The 100, for example, 1000, which is the what? The unstable system formulation, right? And so if this is the case, and then see that if we assign these terms, and so we can observe these times, okay? And so this is how we can draw the Nyquist plot by hand. This is simplest way to draw our equations, okay? And so if you want to draw your or manipulate your Nyquist plot, and then you can use the what? These cases with the what? With in these terms, okay? Also just see that this is the 1000s values in here, but also we can use the what? For the stability region. For the Nyquist plot, determine stability using Nyquist automatically in here. For example, we can define the omega is in here, log space 1, 2, and 1000 points. This is similar to 0.1 to 100 rad sec, right? And so we can define the k values as a range, line space with the what? 0.1 to 200, right? And 100. So from the 0.1 to any point with 100 points, okay? Or the 200 points in here, okay? After that, we can check the or assign the k is equal to the k values in here. We search the whole parameters of these terms in here, just like this one. And so we can take these parts as equals to this one, okay? These are the basic notation for the real and the imaginary parts. And after that, we shall check to the what? The distance or the absolute values of this term. SQRT form is the what? The real part dot square minus imag part dot square, right? But with one basic difference. If we have the real part, we cannot encircle the R Nyquist plot, which means that if I add the -1 in here, and so the distance must be equals to this one, okay? And so the minimum values of this distance returns to the what? The R stability region. And so the current, mean, dist, and IDX can be given with what? The mean distance, okay? And so in this case, if the current, mean distance smaller than mean distance, and then the mean distance is equals to what? The current mean distance, and the critical K can be assigned with the K, and so also the critical point can be assigned with the GS IDX, right? Okay. Also, if the current mean distance smaller than equal to 1e minus 3, and then we can break, because to check if the distance is 0 or very close to 0 in here, because this break can be used with what? The real part. For example, this distance must be smallest, but with what? The +1 term, because we should closing to the what? The -1 in the real part. And so if I put the what? The +1, and then this minimum creates the what? The critical K point, or the last K point, to satisfy the what? The stability, okay? And so this current mean distance also given in here, okay? And so we should write the what? The critical K, and also we need to give the what? The real critical points, critical point, and the IMAC point. We can automatically find the what? The stability of this system. Current mean does not read in here, and so what is this code? Which part? 249. Current mean, yeah. Okay. Dist. I'm sorry. And also mean distance is given nothing here. Mean distance must be equal to the infinity in the first place, okay? So no, it's not the case of these terms. Okay. In this case, mean distance at every time is calculated in here. Why? So we need to check the R code in here. Mean distance, I'm sorry. And so if I run this code, the critical code is the what? The 119.2323. And so the real part of this system is the -1, and this is the imaginary part, okay? And so we exit to what? The -1 at the left hand side of these codes, okay? And so we can easily check the R system is stable or not in here, just like this one. Also, maybe we can change the what? The R system, for example, this one, or we can add the another terms in here, just like this one. It's the 1. And so if I check the codes, and then the critical K is equals to what? The 54. And so this is the automatic way to what? To find out your stability region in the what? In the Nyquist plot diagram. This is important, and this is the easiest way to what? To Nyquist criteria. It's not a standard code, but you can use this code to what? To automatically tune to the what? The stability region of your codes, okay? So now we must give another topic about the what? About the frequency domain, okay? Which is called to the what? To the gain. and fuzz margin. Guys, these two important concepts about to frequency response analysis. Okay, first of all, in frequency domain, these concepts are important for stability of the system. Okay, but what is the meaning of the gain margin? We need to define it. The gain margin is that amount by the system gains, just like the K in here, can be increased without or the before it reaches instability. For example, just remember the previous example in here. This is its. I'm sorry. This is its. K must be equal to the what? The 120 values. But we can select the what? The 50 value. And so we have the margin to what? To select up to 120 value. Okay? And so, how can we analyze this gain margin using the Bode plot for your system? Because we can automatically detect what the last stable values of the K, but we can just also utilize the Bode plot to find out the gain margin. Margin means that the limits or the boundaries for satisfying any condition in literature. But in the gain margin, which means that we can use the K50, but K can be increased up to 21. And so this range is called the gain margin. And so we have important properties in here. WPC, crossover frequency in here. At the what? The minus 180 fuzz for the what? The open loop system. Just remember the Bode plot. At this case, we have the crossover frequency values in here. And so the gain margin in the decibel form can be calculated with what? 20 log 10 and 1 divided by JWPC, okay, and times HJWPC, okay. This is how we can utilize or find the gain margin of the system, okay. And so this is the crossover frequency for the what? For the gain margin, okay. And so WPC is called the what? The frequency value at 190 degree fuzz. And also we have another important concepts in here, the fuzz margin. Additional fuzz or lag required to bring the system to the brink of instability at gain crossover frequency. Just see that this is directly related to what? The gain, but in the first place the gain margin is directly related to the fuzz crossover frequency, but the fuzz margin is related to what? The gain crossover frequency. This is important, WGC, where the magnitude of open loop TF is unity or 0 decibel. Okay, as we can conclude that the larger fuzz margin, better transient response, and the more robust in here. For example, if we have the greater number of the fuzz margin, and so we can transform, or we can set our system better, creating the transient response, or we can manipulate the transient response easily, and this is more robust in here. And so we can calculate these values based on this information, but it's important to solve the example in order to understand these concepts in terms of the what, in terms of the frequency characteristics. Okay, this is the easiest way to learn. And so the example, and then assume that you have the system GS is equals to what? The 50 divided by S plus 10. Okay, these are the system. And so determine to what? The gain and fuzz margin, right? So the solution can be written as this kind of information. How we can calculate the manually? By using the what? This GS to determine the gain and the fuzz margin. So first of all, we must start with the what? Open loop TF is GS is equals to the what? 1 divided by S plus 1 square for unity feedback. Okay, so calculating magnitude and fuzz by S equals JW, right? And so then JW is equals to what? The 1 JW plus 1 square, right? And so this returns into the what? The JW absolute value is equals to the what? The absolute W and JW1 absolute square, and so it's equals to what? The W and square root W square 1, but we need to take the square root of square form, and then W square plus 1. Okay, this is our two what? Two magnitude of the R system, just using the complex analysis of this system. Okay, and so also the fuzz can be calculated with what? The JW is equals to the what? The 1 divided by JW. This is coming from the what? The complex conjugate form of these terms. Okay, but we need to plus 1 divided by JW plus 1 square. Okay, because we can add the what? The degrees at this time, because we have the two roots in here, just like this one. And so coming from this equation, 90 degrees minus 2 tangential arctan W. Okay, this is the fuzz margin, or this is the fuzz property. Okay, so at the second case, we need to return to the what? To these times the crossover frequency must be found. First of all, the gain crossover frequency, which is the WGC. Okay, and the magnitude is to equal to the what? To the 1. Our basic condition is that magnitude must be equalized to the 1. because this is the gain crossover frequency range, the limit. If we have the magnitude is 1, the input signal can be transmitted into the output without losing. And so this is the crossover frequency. And then we can write that absolute JWEC is equals to what, the 1. And so we calculate the whole of these things, have calculated W square plus 1 must be equals to the 1. And so W over 3 plus W minus 1 is equals to 0. And so where WGC is equals to what, the 0.682 radian divided by second. Okay, this is the gain margin. And so fast crossover frequency. WPC. GWPC is equals to the what? The 1 minus 180 degrees. Okay? Because it's the crossover frequency. It's the unstable from at that part. Okay? And so minus 90 degree 2 times arc tangential W must be equals to 100 degree. And so the tan minus W is equals to what, 25. And so W 1 radian second in here. But this is the PC. Okay. So how can we calculate to what? To the margin in here with these concepts. Just remember that this is the PC, this is the GC, gain crossover and the fast crossover. And so the margins are the gain margin G, J, W, PC. This is the fast margin crossover frequency is utilized to what? To calculate the gain margin. And so 1 divided by 1 square plus 1 must be equal to what? The 1 divided by 2. Right? This is the equals. And so the dB form returns to the what? The 20 log basis 10 1 divided by 0.5, and so which means that this is the 6 dB. This is the gain margin values of the R study GM. Okay, this is the gain margin. And so also we have the fuzz margin in here. Fuzz margin can be calculated with what? The G, J, W, GC, gain crossover frequency. And so minus 900 2 tan over 0.682, and so this equals to what? The minus 158.52 degrees. And so the fuzz margin can be equalized to the what? To these terms, but we need to calculate what? The 180 degree minus these terms is equals to what? The 21.48 degrees at the fuzz margin. Okay, what does it tell us in here? What's the meaning of these terms? The gain 6 dB means that can be increased the what? This dB without instability. So if we increase the gain or the magnitude of these terms, and then we allow that the 6 dB can be used without instability. Or what's the meaning of the 21.48 degrees in here? This is still not enough for robust solution. This must be higher, up to closing to the what? 180 degrees to the change of the signal. This is not the robust system. This is the result of these things. Okay, but what's the meaning of this? What does it tell us? Just see that if we have the applied signal just like this one, and so is the FT, for example, this is not good enough for the 21 1 degrees. But if we apply the unit step signal just like this one, this is good, but this is not, because we cannot reach this phase degrees in here just like this one. If we have any march or the margin at the phase up to the 198, and so we can drive the system easily in here just like this one. This is directly related to this one, okay? But it's the unit step signal, which means that we cannot affected by the solution of these terms. But this frequency response is affected by this one. This is highly sensitive for for frequency, okay? So how can we prove that all these things in the MATLAB? So and for this system, I'm sorry guys, this is the wrong one. This is equals to 1 s plus 1. I'm sorry. So how can we prove that these conditions in here in the MATLAB? So we can x7 in here just like this one, and so gain and phase margin. So define the numerator in here 1, and denominator is the 1, 2, 1 and 0. This is the exact multiplicated representation of the R transfer function, and so G is equals to the TF and num, and then should be given in here. Okay, and so if I run this code, and then we have this transfer function s times s plus 1 over square. Okay, so how can we find the phase margin? First of all, we can use the body plot in here, body G, okay, and read on. And so if I run this code, and then we will have the body plots on these times, okay, and the characteristics of these terms is given in here. If you are using the characteristics of stability margin, just see that we have the 1 radian in here and 0.682 radian in here, and the phase margin is also given in here. Close-up stable, yes. Close stable, yes. But if you are choosing another step in here, just like this one, and so we may have another solution here, okay? You can note these values from using the body plot, but we can also use another function in here. The gain margin, returning value, the phase margin, returning value, gain, crossover, frequency, and the phase crossover, frequency, okay? And so the margin G can be given in here, just like this one. If I run this code, and then we can comment the whole of these things in here. Okay. So the gain margin is 2, for phase margin 21, gain crossover frequency 1, phase crossover frequency 0.6822. The gain margin is dynamic in here, just like this one. This is the This is the 2, right? But this is the magnitude values, not the dB one. Okay. And so, or we can use the margin G just like this one. If we are using these terms in here with the figures, okay. And so if I run this code, and then we will have the GM 6 decibel PM 21.4 degree at radian, and so all the crossover frequencies is given in here, just like this one. Okay, we can see that these points in here. Okay, and so also this margin can tell us to what stability region of these terms. For example, we can figure a Nyquist plot J, and grid on can be in here, and the plot for the reference 0, 1, and are all okay. And so the legend can be given in here, just like this one, the Nyquist curve and the critical point. -1, zeros. Okay. So the hold off should be given here. And so if I run this code and then the margin at the first place, seeing that this one, okay. I'm sorry, the hold on should be given here. And so we can utilize this information, but see that if we have these concepts in here, the Nyquist curves for the what, for these regions, okay, and so we have the decibel region in here, just like this one, okay, and so we can analyze our algorithms or the basis with what, with in terms of these characteristics of the equations, okay. And so if we have this nomination in here, just like this one, and so this -1 is updated to what, these regions, okay. See that this is the 2 decibel, 6 decibel, 10 decibel, 20 decibel in here for the what, for the stability region, for the what, for the fuzz characteristics curves, okay. This is how we can easily obtain the what, the gain, fuzz, crossover frequencies of the gain and fuzz from the MATLAB utilization, okay. Or we just use the what, these calculations based on the what, the similar explanation of the or examination of the transfer function domain, okay. That's all, guys. This is the end of the what, this is the end of the frequency analysis response of these terms. In the next lesson we will talk about the feedback state or full state feedback definition or the system design in the controller theory, okay.